Ever wondered how the universe bends in response to mass and energy? Welcome to the fascinating realm of relativity. Born in the brilliant mind of Albert Einstein in the early 20th century, the theory of relativity has dramatically reshaped our understanding of the universe and its fundamental workings. To delve into the heart of this groundbreaking theory, let's take a quick tour of its two key components: special relativity and general relativity. Special relativity, proposed by Einstein in 1905, paints a vivid picture of how space and time are woven together into a four-dimensional fabric known as space-time. It tells us that the laws of physics are the same for all observers, regardless of their speed or direction. It also introduces the mind-boggling concept that nothing can travel faster than light. A decade later, Einstein came up with the general theory of relativity, an extension of the special relativity. It describes how gravity isn't just a force, as Sir Isaac Newton had proposed, but a curvature in the space-time fabric caused by mass and energy. Imagine a bowling ball placed on a trampoline, causing the surface to warp. That's essentially what mass does to the fabric of space-time, according to general relativity. The beauty of these theories lies not just in their mathematical elegance, but in their profound implications for our understanding of the universe. They've transformed our views on time, space, gravity, and even the nature of reality itself. But what sets relativity apart is how it marries the abstract world of mathematical equations with the tangible, observable universe. It offers predictions from the bending of light by gravity to the existence of black holes that have been spectacularly confirmed through experiments and observations. As we delve deeper into the peculiar world of relativity, prepare to have your mind bent just like the fabric of space-time itself. So, what predictions does general relativity make about our universe? Well, let's start with the idea of gravitational lensing. When you think of a lens, you probably picture a piece of glass that refracts light to make things appear bigger or smaller. But in the cosmos, gravity can act as a lens too. According to general relativity, massive objects like stars and galaxies have such a strong gravitational pull that they can bend the path of light passing near them. This bending can create incredible cosmic mirages, where light from a distant object is warped into rings or arcs around the massive object. It's as if the universe itself is wearing glasses. Next up, we have black holes. Now, these aren't your everyday holes in the ground. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They're like cosmic vacuum cleaners, sucking up everything that gets too close. The existence of these mysterious objects was predicted by general relativity, and while they're still shrouded in a lot of mystery, we've gathered plenty of evidence that they're out there, lurking in the depths of space. And finally, let's talk about the expansion of the universe. Yes, you heard that right. The universe is getting bigger. General relativity tells us that space itself is stretching, causing galaxies to move away from each other. It's like we're all on the surface of an inflating balloon, moving apart as the balloon expands. And the most mind-blowing part? The rate of this expansion is accelerating. The universe isn't just growing, it's speeding up. These predictions, as wild as they may seem, have been confirmed by experiments and observations. Let's explore how. How do we know that these predictions of general relativity are true? A very valid question, and one that has prompted scientists to investigate and validate Einstein's theory for over a century. One of the most famous confirmations of general relativity came in the year 1919 during a total solar eclipse. A British astronomer named Sir Arthur Eddington embarked on an expedition to the island of Principe, off the coast of West Africa, to test Einstein's bold prediction. According to general relativity, light should bend around massive objects due to gravity. Eddington observed that the stars near the sun indeed appeared to shift their positions during the eclipse, proving that the sun's gravity had bent their light. This was a groundbreaking confirmation of Einstein's theory and made headlines around the world. Fast forward to the 21st century, and we have even more compelling evidence supporting general relativity: black holes. These strange and mysterious objects were first predicted by the equations of general relativity, even though Einstein himself was skeptical of their existence. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. This makes them incredibly hard to observe directly. However, scientists have gathered indirect evidence of their existence, such as the detection of gravitational waves from colliding black holes and the imaging of the shadow of a supermassive black hole at the center of a galaxy 55 million light-years away. These confirmations, along with countless others, have made general relativity one of the most well-supported theories in all of science. Despite its abstract nature and mind-bending predictions, every single test we have thrown at it, general relativity has passed with flying colors. So, the predictions of general relativity have stood the test of time. But what does this mean for us, and why should we care? Well, as we'll see in the next scene, the implications of relativity go far beyond the realm of pure science and have profound effects on our everyday lives. Opening. Why does the theory of relativity matter in our daily lives? Well, the theory of relativity, proposed by the great physicist Albert Einstein, has far-reaching implications that extend beyond the realms of theoretical physics and astronomy. While it might seem like a concept designed for scientists and researchers, the theory of relativity actually has a significant impact on our everyday lives. Let's take the Global Positioning System, or GPS, as an example. We use GPS technology almost daily, from navigating city streets to tracking our morning runs. But did you know that the accuracy of GPS is deeply rooted in the principles of relativity? To provide precise location data, GPS satellites, which are moving at high speeds and are far from the gravitational pull of the Earth, need to account for both special and general relativity. Special relativity comes into play because the satellites are moving relative to the Earth. This movement causes their clocks to tick slightly slower than the clocks on Earth, a phenomenon known as time dilation. If this wasn't accounted for, GPS coordinates would be off by about 7 miles per day. Now, let's consider general relativity. The strong gravitational field of the Earth slows down the clocks on the satellites. This is because, according to general relativity, gravity can bend space-time, causing time to tick slower in stronger gravitational fields. If this effect wasn't corrected, our GPS devices would be off by an additional 45 miles per day. So, in order to maintain the accuracy of GPS technology, both these relativistic effects need to be taken into account. This is a clear example of how the seemingly abstract and complex principles of relativity have practical implications in our everyday life. The theory of relativity has also paved the way for understanding and exploring the universe. Concepts like black holes, gravitational waves, and the expansion of the universe all stem from this groundbreaking theory. Closing. Indeed, the theory of relativity, while seemingly complex and abstract, has profound implications for our understanding of the universe and our daily lives. The theory of relativity has left an indelible mark on our understanding of the universe. It has shifted our perception of space and time, painting a picture of a cosmos that is far more intricate and interconnected than we could have ever imagined. This theory, proposed by Albert Einstein, has not only stood the test of time, but has also shaped the course of scientific exploration. From the bending of light by gravity to the existence of black holes, the predictions of relativity have been confirmed time and again, reinforcing its stature in the scientific community. It plays a critical role in technologies we use every day, like GPS, and has spurred on countless scientific advances. As we continue to unravel the mysteries of the universe, the theory of relativity will undoubtedly remain a cornerstone of our quest for knowledge. So keep questioning, keep wondering, and keep exploring the cosmos through the lens of relativity.